Okay, so good afternoon to all of you. Today we will learn little bit about operational amplifiers. Okay, so to start with, let me start the recording. Yeah, so to start with, this is the symbol for an operational amplifier, wherein we have two
Sir,
inputs.
recording is not yet started.
No, it started. Okay.
Yeah, now it started.
Yeah. So there are two inputs. Okay. One is known as an inverting input. Okay. So you represent it as a negative symbol out here, and then you have a non-inverting input. Okay. So that is a positive out here represent, and then it could have an power supply plus and minus. Okay, V minus. So in certain designs you have plus volt and minus volt, or you could have an plus volt and 0 or a ground also out here. Okay, but more often than not in operational in analog circuits we use plus and minus voltages. Okay, so this is the symbol, and this is the output. Okay, so this 2 3 4 7 6 that comes from one of the very widely used op-amp, which is 741, in which these are the input pins. Okay, 3 is the inverting input, and plus the pin number 3 where you give the non-inverting input, 6 is the output, 7 you give the power supply, plus power supply, and the minus power supply at pin number 4. Okay, so these are just the pin numbers of a standard 741 op-amp. Okay, that's
Sir, why is 5 not there?
no, 5 and 1 and all, they're used for different purpose. Okay,
Different
for
purpose.
offset
Okay.
adjustment and all. So these are the main inputs. These are the main inputs. Okay, it's an a 8 pin IC. So other pins are used for different purposes. Okay, total there are 8 pins in that. Okay, but this is just a symbol. Okay, forget about the pins. In CMOS, we are going to see the circuit inside this and what is going to happen. Okay, so there are certain requirements of an op-amp, an ideal op-amp, and how should it be? It should have an infinite gain. Okay, so the gain is actually, if you see the amp, whatever input is available at 3 minus the input what is available at 2. Okay, multiplied by the gain should be available at the output. Okay, so this does the subtraction of these two signals, like different amplifiers what we studied till now. Okay, so that can be called as an operational amplifier, although it doesn't meet all the specifications, but a common differential amplifier which we have learnt and can be called as an operational amplifier. Okay, now if you see here, the gain should be infinite for an ideal op-amp, but then in actual practice it is around 20,000. Okay, so the gain is around not 20,000, it's around 200,000 or 2 lakhs or. Okay, so that is it should have infinite input impedance. Okay, so but for a simple differential amplifier which we learnt, we didn't have these kind of gains, right? So but an ideal op-amp should have an infinite, and practical op-amps do have this range of this is the kind of an gain which they will have, and then it should have infinite input impedance. That means no current should flow into the inputs. Okay, so that is generally even for our differential amplifiers, since what we learned till now, since we were giving the input to the gate of an FET. So the impedance was very high, almost infinite. So it is up to the power of 10 to the power of 12 for an FET. So it's very high. You can see that, right? So zero output impedance. Okay, that means the output gain should not depend on the load. Okay, so in our normal differential amplifier which we learnt, and obviously the output load had an say in the total gain, but if you remember when we learnt about the common drain or a source or a source follower, there in that case the requirement you could connect low load. So so you can think of an operational amplifier, the output stage should be a common source amplifier, common drain amplifier, okay, or a source follower, so that it can so that you can connect low loads also. Okay, low resistances, zero. We generally call it as high load, which high load means low resistance, which takes lot of currents. Generally it should be able to give these kind of currents, to 5 to 25 milliamperes of current, okay, at the output stage. And it should have infinite bandwidth. That means it should be very fast. These are all ideal conditions, but in actual practice the bandwidth will be only few megahertz, and the slew rate will be 0.5 to 20 volt per microsecond. So whatever is written in red out here is the ideal conditions, and whatever is written in the black is practically what we achieve in these circuits. Okay. So,
Sir, when you say high load, that means low resistance.
yes,
It
correct.
consume more
Correct.
current.
Correct.
Okay.
So now if you see here, this kind of circuit, if it is open like this, it is actually of no use, okay, because a small voltage, okay, difference out here will take this to saturation, because V out, if the gain is 20,000, if you give 1 millivolt also, it will go into the VCC or ground, right, depending on what which is greater or that. So outputs will be either plus VCC or minus VCC, maximum voltage it will give, because the gain is very high. Small difference in input, so this is not generally used without feedback. This is an open loop configuration. So here we very rarely we use op-amps. If you want, you can, if you want to use it for as a comparator, that you give a reference signal here, and if the signal is going beyond the reference voltage, the switch to 1, logic 1 and logic 0. In those kind of applications you can use it in open loop, but generally for analog applications we generally don't use it in the open loop configuration. So how do we use it then? Then we generally give some kind of feedback. So in this particular example I have shown an unity gain feedback. So here the output is given to the input out here. Okay. So what happened? Suppose initially it was 0 here, it was 0 here, and it is 0 here. It goes to 1 millivolt here. Suppose a small increment, say 1 millivolt. What is the gain? It is initially it was 0 here, 1 millivolt into 10,000 or 20,000. So it will start going, but as it keeps increasing, the moment it comes to 1 millivolt, and I have 1 millivolt here, 1 millivolt here, so it won't further amplify anything. So this will get stabilized when V out is equal to V in, okay, because this is an feedback is given like this here. So whatever is the V in variation, the same thing I will get it out here, right. So this is known as unity gain, because the gain is 1, right. So this is known as a negative feedback.
So sir, this unity gain, are we using that same formula which we learned in the last class, 1 by 1 plus A beta?
No,
negative on the for the negative feedback.
Yes, yes. We can say that where with regards to feedback, it is an A beta. We are giving here.
So in that case, if it is unity gain, you mean to say the A beta will be 0?
No, A beta will not be 0.
If it is unity gain.
No, beta is 1, A is high. Let me this feedback V0 is being given, okay. The feedback is A divided by 1 plus
This
A
is closed
beta.
loop gain, right?
Yeah,
this will be closed loop gain.
Closed loop
X0
gain.
by XS is
Here
equal
beta
to,
is equal to 1 in this case, because output I am giving as it is to the input, and A is very large, okay. So bottom it becomes A divided by A beta. So AA gets no, beta is equal to 1. So AA, so on the numerator you have A, in the denominator you have A, so the gain is 1. So this is the configuration where I have the gain as 1. Is it okay?
so it will be 1 by beta then.
No. Beta is 1 here in this case.
Correct. So
it is 1.
Beta is 1 and 1 by beta is 1.
1.
Correct, right?
Yes.
Because A is large.
Yes.
Okay.
Okay.
So the gain becomes unity. Okay.
Yes. Right. Now, then if the same signal is available at the output, what is the purpose of this amplifier? Can anybody say?
Can you repeat, sir?
Buffer.
If the same input is available at the output,
Buffer.
yeah, correct.
It is work as a buffer, sir.
It will work as a buffer because the load will be driven by this amplifier from this power supplies, whatever is available. Okay, if you connect a load here. So, input and output are isolated. Okay, so this will offer an high impedance to the input, whereas here you can. So, this acts like an buffer out here. Okay, so this is how an op-amp is generally used. This is one of the configurations. There are other configurations also. So, this is again the same thing which I explained. So, you can connect a low load out here, and then it is. And as an V in changes, so the output also will follow V in. Okay, so this can be used as a buffer without burdening the V in with any current. So no current will be taken from V in. Okay, so this is what an op-amp does in unity gain configuration, right? So,
Sir, one doubt.
Yeah.
So if we take this output signal to the negative inverting input, then in that case, if we look at this circuit from the operational point of view, then the difference signal will not be zero.
No, actually, no. This will try and follow this signal. So they will be. No, you can assume that these two signals will be same.
So it like op-amp also work like a differential amplifier.
Correct.
So it will take the differential input for amplifying.
Correct.
So if the output signal is also similar to the input signal, then this different signal becomes zero in that case, I think so.
Suppose this signal is say 10 millivolt. It is 10. Okay. What happens if it starts falling below 10? This will become, say it becomes 9. So this becomes 9. Again this will be pushed to 10, right? So it will become stable that way.
No, that is correct. But how, like if it is used as an amplifier, then in that case, if the two signals are same, then the different signal will be zero. So output will be zero in that case.
No, yes. So that's what initially. Suppose this is 0. Okay, this is initially 0. This is 10. This is 0. So this will start going towards 10. The moment it reaches 10 volt, okay, I have 10 here. Okay, so then you can say this will start falling to 0. Right, but that cannot happen because the moment it starts slightly below, because of the high gain, again it will reach back to 10. So in an equilibrium condition, you can consider that these two voltages will be same.
Okay. So like if it is same, then difference is zero. Then output tries to reach to 0, but still the negative feedback is there, and that decreased value is again difference we take. Then it is non-zero. So it will again at equilibrium it will not be 0.
Yes.
Okay.
Right. Okay. Practically speaking, okay, if this is 10 millivolt, okay, here, okay, it will be 10 divided by 22 lakhs, something like that. Correct. That is a very, very small voltage, or you can assume that this is both following each other. If you assume this to be infinite, then you can assume these two input voltages are following each other. Is it okay?
Sorry, what you have explained this? 10 divided by?
Suppose this is 10 millivolt, right? This is 10 millivolt, right? This gain is 20,000, right? So this will be, right, this difference will be, right, 10, because it is 10 here, right, 10, this difference VD will be 10 divided by 10 millivolt divided by 20,000, right? So that is very, very small, right? So you can assume these two voltages are almost following each other,
Okay.
right? That way also we can think. Okay. So there are certain golden rules for op-amps. First is we assume that the inputs, the terminals don't take any current. That means there is no current flowing into the input. Okay. So generally, it's if it is a MOSFET, obviously we know it is in a gate, so no current will flow. So that is the for analysis purpose. So that is one. Second is we assume that these two voltages are equal, this voltage and this voltage. For a high gain, obviously, and a finite output, this will be close to each other. Okay. For an infinite gain, for an ideal op-amp, this will obviously will be divided by the gain will be 0. So for any negative feedback, these two terminals, they will follow each other. So if you apply these two rules, then you will be able to analyze any kind of circuit, how it works. Okay. So the first one is an inverting amplifier. So what it does
sir?
is, yes, tell me.
Excuse me. So can you explain that one important note which you have written in
Where?
previous slide? Previous slide, sir. Here, sir, you have written one op-amp.
An open output terminal source sinks current set will not like the inputs that have no current. Okay, that means this output from the output node, okay, this can give current to the load, or it can take when the signal is falling below, suppose it is a capacitor and there is a requirement of discharging it will source or sink the current, right? But it will not affect the input voltage. It is isolated. The input is isolated from the output. So these currents will come from the from the power supplies. Is it okay?
Okay. Okay. Sir.
Like we learnt about the differential amplifier, right? So we are not drawing any current from the input, right? Because that the inputs are seeing the gates of the transistors. So that is like almost like an open circuit. So the output currents will be from the power supplies.
Sir, I have one more question in this same diagram. Any reason why we don't give this negative feedback to this positive terminal?
Then it will become a positive feedback. Okay, and if you give a positive feedback, then it will work like a comparator only. It will either be VDD or ground.
Okay.
Okay. Suppose this is positive and this is negative. Okay, let's assume that way. Okay. Now initially suppose it is 0 and this is going slightly high. Okay. So the output will be minus and it will go towards negative, right? If it is going towards negative, this voltage will go negative. That means the difference will be more. So it will rapidly, within no time, this will go to minus VSS.
Okay.
So there is no, it will either give plus VDD or minus VSS. Okay, so this will act like a comparator. So there is no use of that. There's not only we use these as comparators. Okay. Especially in ADCs, when we have to analog input, we are comparing it with some V reference and all. So we use it in open loop configuration. So comparators are made up of open loop. Otherwise, amplifiers are generally negative feedback.
Okay.
So this is an first configuration where it is known as an inverting amplifier. Okay. So what an inverting amplifier does is, see these two input terminals are common. Okay. Same potential. So that means you can assume this is going to be a ground. Since it is negative feedback, obviously these two will be same potential. So there will be a virtual ground here. It is known as virtual ground. Okay. So this will be at ground. So now the current which is coming here, okay, it cannot go here. So it has to go up only. So there is. So now you can equate these two currents. Okay. What will be this current? This will be V in divided by R1. Okay. This current. And what about this current? This current will be V out. Okay. this current is going like this. If I have to, that is 0 minus no, where is it written? Okay, so let me write, this current is like this. So this I can write as V in divided by R1. Okay, and this current is going to be minus V out. Okay, because it is 0 here, this current has to flow like this, so it will be minus V out by R2. So if I write V out minus V in, it will become minus R2 by R1, right? So that is the gain of this amplifier. So it is an inverting gain. So whatever gain you want, you can, so this is the gain, minus R2 by R1. So whatever gain you want, you can adjust these two values. Okay, so you can do that. So, but it is negative. So obviously, if you have a positive signal coming here, so you will have an amplified signal like this in the output. Okay, so but
Sir, in the assignment, we have to show how much gain. Any?
No, did I say op-amp there? Op-amp design is given.
Yeah, two-stage op-amp design.
Yeah. Okay.
Two-stage op-amp.
You can have around 100.
100.
Okay, 10 into 10. That is good enough. Okay. So this is okay. So another thing which is an important out here is again here for analysis purpose we are writing this IF. Okay, but this doesn't mean that from the input side this current will be given to the load. Here we have the load, right? Okay, so the load will be driven from the VDD or the ground. Okay, so the input is not going to drive RL. Okay, so it will be from VDD and VSS also. So the gain is minus R1 by R2. Okay, so we can have now. Suppose this is plus 15 volt and this is minus 15 volt, right? And I put an R2 as 10 and R1 as 1, and if I give an sinusoidal signal here of 1 volt, what will be the output?
Minus 10 volt.
Okay, it will go from if I am giving this signal from 1 to minus 1, okay, the output will be like this. Okay, it will go from minus 10 to 10. Okay, now suppose if I give it to 100, what happens? Will it go to 100?
No.
Yeah. So you will probably get a square wave like this. Okay, this will get clipped actually. This will be a small sinusoidal signal. Okay, you can. It will get clipped to minus 15 and this will get clipped to 15. Okay. So this is what this. So this is known as an inverting amplifier. Okay, you could have a non-inverting amplifier.
Sir, can you explain that virtual ground concept? Why we call this?
Because we are telling this and this terminal, they will follow each other. Okay, so this voltage will be close to ground, but there is no actual ground connection at that terminal, and that is the reason we are calling it as virtual ground.
Okay.
Right, because this inverter is in an negative feedback configuration, the voltages at plus and negative will follow each other very closely. And since on the positive side we are giving a ground, so we will say ki on the negative side also there is a virtual ground available. Okay, it is not a physical ground available. Okay, it is because of the feedback, the amplifier gain, it will drive the currents in such a manner that this voltage will come close to 0. Okay, that is why we call it as.
So sir, that means in the schematic we don't really ground this.
No, no, we don't ground it. Okay, schematic will be like this.
So this is the property of like op-amp, like both the inputs are almost same.
Yes.
Inverting in.
Yes.
Okay.
Yes, that's the property of the op-amp. That is provided you give a negative feedback.
Okay.
Sir, but
and there is one more condition. Okay. Okay, when these two signals will not be equal in these cases, as long as the output, okay, as long as this is in within the linear region, these two voltages will follow each other. Okay, and when it is not able to, it is getting clipped like this here, then these voltages will differ in that case.
Okay.
Okay. Yeah, tell me. Because you will see here,
Sir,
if you apply the 15 volt out here and you put a virtual ground here, then this equation will not be satisfied in that case. So that is, so whenever it is going to saturation, if it is getting clipped, then these voltages, then this negative feedback has got saturated. Then this will, the difference in voltage will start creeping in these two voltages. As long as it is in the linear region, they will be same. Yeah, tell me, sir.
Sir, but if these two inputs are not equal, what will happen to the gain? If it is 15 minus 15 you have given there, right?
Yes, that is the power supply.
No, sorry, on the input side I'm saying, not that.
Input side,
So,
I have
yeah.
given 1 volt, right? So it will be here it will be virtual ground. These two voltages will follow each other.
Oh, okay, got it. Okay.
This 1 volt will be dropped across this resistance.
Okay.
So obviously, if you don't want to load this input, you will have to use a large resistance here. Okay. Otherwise, it will load the input resistance. So this is not going to drive the output resistance, okay, but it will drive this resistance. So you have to be careful with putting resistance here. You have to put a large resistance here. So I can have a non-inverting amplifier also. So this is the configuration. Okay, here I have given a V in here and on the positive terminal, and I have given a negative here. Is it positive feedback by any chance?
No, it's negative.
Yeah, it is negative feedback only, because from the output I am giving it to the negative terminal. So it is still a negative. Okay, it is non-inverting, and hence I am giving the input to the positive terminal. Here I am giving input to the negative terminal, and feedback also negative. Here I am giving input to the positive, so it becomes non-inverting, but it is still a negative feedback. Okay, so now this is a V in. Okay, now what would be the current flowing like this? Okay, that current will be V in divided by R1. Okay, and that current has to come from here. Okay, because into the op-amp no current can flow. So that current will be V out. Okay, and this potential is V in here, V in, and divided by R2. Okay, so now you can take this V in term there and V out by V in. So you will get this V in is equal to 1 plus R2 divided by R1. V out is equal to, so this is the gain, 1 plus R2 by R1. This is the gain. Okay, but there is no negative here. Here it was negative minus R1 by R2. Here it is 9. So if I give a signal out here, right? So I will get an amplified signal here out here at the output. Okay, so this is known as non-inverting output. Okay, some characteristics which you got to remember out here is here is a gain less than 1 permitted. Can you target a gain which is less than 1 also for inverting amplifier? Voltage gain. Right? It's possible, right? If you keep R2 less than R1, the gain will be lesser. So you can have less than 1 gain also, right? Voltage gain. But there will be power gain, because if you are connecting a low resistance, high current will flow here, right? So I square R. So there will be power gain. Okay, but you can have an voltage gain which is less than 1 in a non-inverting, because it is just a ratio. But for a non-inverting amplifier, you can't have an, because it is 1 plus R1 plus R2. So the minimum gain is 1, or you can have gains more. So anyway, from 1 to infinity, you can have any gain. Okay, here you can have anything from 0 to minus infinity in this configuration. Okay, here it is 1 to infinity. Okay, so this is known as non-inverting amplifier. Okay, then
Sir, here
we
are also considering the same concept what we consider for virtual ground.
Correct.
That's why we have done V in upon R1.
Correct. We are assuming this voltage will be here V in. Same. Okay. This equation comes from that only. Okay, that only, like I said, if I go back, there are two golden rules. Okay, one, there is no current which will flow into the inputs of the op amps. Second, the both the terminal voltages will be same. Okay, so this is the rule everywhere we will apply for analysis of op amps. These are the two rules which we are going to apply everywhere. Okay. Okay, this is a summing amplifier. Okay, now what it does is, now if you see here, there is a current flowing like this here, there is a current flowing here, here I have a virtual ground, so this current has to be like this. Okay, it has to flow like this, right? So I can write V1 divided by R1 plus
V2 by
R2 is equal to minus
V out
V
by
out,
RF.
minus, there will be minus 1, okay, by RF, correct. So if I keep all these three resistances same, right, then I will get V1 plus V2 is equal to minus V out, okay, because it is inverting, it is adding these two signals, but it will also invert, okay. But if I keep an R1 and R2 same, if I keep R1 and R2 same and RF different, then I can get gain also, like output can be V out will be, okay, something G into V1 plus V2. I can get some gain also, isn't it? Right? It will be RF divided by R1, in case R1 and R2 is same. Then this G will be RF divided by R1, right? So I can have gain also. If I keep this same, then I will have unity gain also, right? Is it okay? Right? Okay. So this can be used for like D2A converters also. Like for digital, you have, suppose you have 101. This is what 1 into 1, 0 into 2, and then 1 into 4, right? So if I change these values, if I put R is equal to 1K, this I put as 2K, then I put as 4K, right? So they will get divided by the weightage, whatever weightage. So I can use it for digital to analog conversion also. So if you see some D2A converter circuits, so these summing amplifiers can be used here, right? So, suppose this I am using as 1. So this current will be V1 into 1. This I am using as 1 by 2. Okay, so it will become 2V2. The next I can use R is equal to 1 by 4. So it will become 4V3. So each digital input can be is going by a factor of 2, right? So that you can do by adjusting these resistors also. So these kind of amplifiers can also be used for D2A converters. Okay, so this is known as a summing amplifier. Okay, so now we can have something known as
so
yeah, tell me.
In the previous slide, sir, I have a question.
Yeah.
So we have written one question there. Can we have any number of summing inputs? Can you please explain that part? I think it's not possible, right? We can't have n number of inputs, right? Summing inputs, I mean.
Yeah, we can have, right? That's what it says. Here we have talked about only 2. Can we have 3? Can we have 4? For an 8-bit, I can have 8. That's what it says.
Right, sir. So let's say I will go for 100 or 200. Can we go for that? Like,
yeah, I mean,
we should take care of some. Yeah.
That will consume more power, right?
Yeah, I mean, it's not an issue. Like if you have an 8-bit and a D2A converter, why I have written this like this is because I have shown only 2-bit, and say suppose I want an 8-bit or a 16-bit data, so I can make an 8-bit D2A to converter or 16-bit A2A converter. Okay.
Right.
Okay. Now this is a difference amplifier. Okay. Now what it does is V out is an R2 divided by R1. Okay. And then it does V plus minus V minus. Okay. So how did I reach this equation? Again you do the same thing. This, what will be this voltage? Can anybody say what will be this voltage?
It should be R2 divided by R1 plus R2 into
Yes.
V plus.
Yes. So this, right? This is the voltage. Same voltage is available here now, right? Now I can write the current equation, that is V minus this voltage is equal to V out, okay, or this voltage minus V out divided by R2. So if I write that equation, I'll reach this. So this is known as a difference amplifier. Okay. Now this for that to have you should have R1 R2. Here also you should have R1 R2. So if you do that, then you will get V out is equal to this. Okay. What we did, this was V plus. We found out V plus. Then we applied this V plus here and we equated this current with this current. Okay. And since we have used R1 here, R2 here, R1 here, R2 here, we land up at this equation. Okay. So it is what
Sir, where is this differencing amplifier used in what applications?
if you have to analog applications, if you have to take the difference of two signals, whenever you have to take difference of two signals,
Okay.
right?
Sir, why voltage divider is used as one of the terminal for differential amplifier?
Here,
This divider.
only then if you use R1 R2, you otherwise you won't reach this equation like this, right?
Okay.
So this R1 R2, this R1 R2, if you match it, only then you will. This is V out, this is gain, and this is the pure difference between these two signals.
Okay.
But sir, without this voltage divider, we can have a difference amplifier. Only the thing is, this equation will be different.
Yeah, they won't cancel out. If they don't cancel out, then you can put an here in this equation, R2 is equal to 0. Right? Then then this gain will become 0.
But sir,
no.
this is different equation. Like when we consider R2 equals to the above negative feedback R2.
That is what
then
is considered
directly
here.
we directly can't put here R2 0.
Yes. We can put R2 is equal to 0. Okay.
No sir, my question is like if we don't keep this voltage divider or and only keep this R1 and directly apply, then it will also work as a difference amplifier. There is no compulsion rule of having this voltage divider.
No.
Yeah, only thing is equation is different.
See, it will become equation. See, if you apply V plus here, okay, the current here, okay, will be V minus, okay, minus V plus, correct,
by R1
by R1 is equal to, right, V out, right, this current. So this will be V plus minus V out by R2. Correct. So you won't get V1 minus V2. So because these are different, they don't get you won't reach at V1 V plus minus V minus it if you do that.
Okay.
So that is the reason.
There is no current in non-inverting terminal, so voltage difference will not be in inverting terminal or non-inverting terminal. We will not get V1 minus V. Difference will not get.
We will not get the difference.
No sir, but if we keep this, so if I remove this voltage divider R2 and only keep this R1, and if I keep this R1 and R2 to be same, in that case it will be there.
No, there will be no voltage difference because there is no current. So R1 will not come picture. R1 will not. If you will remove R2, then no use of R1.
It will be V1 only here.
V plus.
Yes, V plus. Exactly.
No sir, but here you told like we will not get V plus minus V minus.
Yes.
But if we keep R1 and R2 equal, then we will, from this equation we will get that.
Okay. let's try and do that. Okay, you are saying there is no R2 there.
R2, yes.
Okay, so V minus V plus. This is the voltage.
Yes.
Divided by R1 equal to
V out minus
V plus.
V out minus.
No, this current, right? This current is going to be, so it will be V plus minus V out by R2. Right now, you have to keep R1 and R2 also the same.
Yes.
In that case, yeah. Then there will be no gain. It will be a unity.
Okay.
Right. Correct.
Then.
Sir, B minus and B plus will be same here in this case, because if we will keep R1, then B plus and B minus will be same. Then
no. B plus will
difference.
be here.
Correct,
B minus is here. So there will be current flowing like this.
Okay, correct.
Correct.
But sir, if we take this V plus right,
again still it is not coming same. Actually V minus, okay, so it will give a V minus. If you take this here, it will be a 2V plus is equal to V out minus V out. So you are not getting a correct differential output, right?
Correct. Okay.
There will be an issue there.
There is a need of this voltage.
Yes. Okay. Now you can use this as a differentiator or high pass filter. Okay, it's all the same. Now I have a capacitor here, and I have a resistor out here. So if I Q is CV, right? This is the, so dq by dt will be C dV by dt, right? So this current, okay, this current out here will be C into dV in by dt, right? This current, and this current will be minus V out divided by R. So I can write V out will be, okay, a minus RC into, okay, dV in by dt. So this is what the equation which is written here, right? So it is differentiating the input, okay, and RC is the gain. Is it okay with all of you? Okay, so let me now ask you a few things. If I give a square input, what will be the output?
0.
Here.
For every rising edge or falling edge, you'll have a pulse.
Spikes actually.
Yeah, spikes. Okay, what kind of spikes? Here, what would happen?
Only at rising and falling edge, we should be able to see some spikes.
Okay, because this is a differentiator, so constant, here it is constant, here it is constant, so output will be 0. What happens to this spike?
A negative spike. For positive
you will get a negative spike because there is a negative out here, and for the for this negative edge you will have a positive. Again for this for this positive you will have a negative edge. Okay, like this. Okay. Now for a sinusoidal signal, what would be the output?
If it's in pass band,
minus.
The sign will become cos and minus cos. Okay. So accordingly, there will be a phase shift in this signal. What is available here? Okay. So yeah, it's written here. Sine will become minus cos. So that is it. And now why is it known as a high pass filter? Is if you see here, okay, the gain is RC, right? So okay, now like for V0 sine omega CT, if you differentiate it, you will get minus RC, and then omega is also will come in the opposite. So for high omegas, okay, if omega is equal to 0, then this will become, output will become 0. If omega is equal to high, then this is going to give a high gain. So obviously this for small signals, this will become a DC blocking Okay, so small signal. So this is also an high pass filter. Okay, is it okay? Why it's an high pass filter?
Yes.
Okay. Now if I swap these positions of the resistor and the capacitor, then it becomes low pass filter. Okay, in this case, this equation I can write it as dV out, okay, into C, dV out by dt, okay, minus of that is equal to V in divided by R. Okay, now dV out will be what? Integral. Okay, integral of, so but this R is in the denominator, so this C will also, so I have an RC in the denominator here and integral V in, and obviously there is a negative sign also, so this will act like an integrator. Okay, now there is a negative sign also is available here. Okay, and since this offers, okay, less impedance at high frequencies, obviously you do the same analysis here. Omega will be in the denominator, and hence for high frequencies, okay, you will have high gain. For for low frequencies you will have a high gain, and for high frequencies it will have, this will offer a high impedance, so there won't be any gain. Okay, so that is one option. So what happens if I give a square input? What will be the output?
Rise time will increase.
Yeah. So if I keep an R sufficiently large, what happens?
Sinusoidal kind of.
Not sinusoidal. Linear. It will be triangle. Right? It will go like this. For the positive cycle, okay, of this, it will go towards negative, and for the negative cycle it will go towards the positive. Right? So if you keep R very large, very small, then it might go very fast and it will get saturated. So you can get an trapezium kind of wave also. Okay, but if you keep R very large, then you can get a triangular waveform. So you can use these kind of circuits to convert square wave into triangular wave. Okay, so that is there. Okay, now let's before we take on the design of the op-amp, let's try and understand some of the specifications of an differential amplifier. One is a differential gain. Okay, that we saw, that is difference, how much time it is going to be. So it is like 20,000 and all. 20,000 will come to what? Close to 100 dB, right? So these are the ranges. Okay, in dBs. 80 to 100 dB. Okay, so that is the kind of a gain, difference gain, and also the common mode gain. Okay, so that typically will be around 20 to 40 dB in practical CMOS circuits. Okay, so then you have the CMRR, right, common mode rejection ratio, which is the this gain divided by the right, differential gain divided by the common mode gain. Or in dB, when we divide, we subtract, right? So you will get around 40 to 80 dB is the CMRR. Okay, so that is the generally figures what we get in op-amps. Okay.
Sir, why so much common mode gain for op-amp? Like
these, right? Because you see, when you have when we did the analysis, right? If you see there, the current sources and all, they are not ideal, right? So they will generate a common mode gains also.
Okay.
Right. So that will be there. Okay. Now you can have an see there are a lot of other criteria also. Now you can keep cascoding the current source one above the other. Okay, to increase the resistance and make it close to ideal. But if you do that, you will consume more power, you will consume more headroom, right? So it is all a mix and match. So there will be so many specifications. So to meet that, so you will have to compromise somewhere, correct? How to reduce the common mode gain? If you remember, what that tail current resistance has to be increased, right?
Maximum.
Right.
Maximum.
So for that you can have a cascode structure, right? then the headroom will get affected, correct? So input common mode range will get affected. So those are the issues. Yeah. And then you have something known as power supply rejection ratio. So when you give an same input to both the terminals, okay, and this should be an output should be 0, but if you vary the power supply, okay, output should not change, but it doesn't generally happen. Okay, a small change will happen because actually the operating condition of the biasing conditions will change, because of which the gain will change, and hence it will get reflected at the output. Okay, so this is the kind of that is known as PSSR, power supply rejection ratio. That is a gain divided by the gain differential gain divided by the gain due to power supply. Okay, so this should be small. Okay, so typically,
sir, why will there be gain due to power supply?
Actually, when the power supply changes, the output should be stable, but it won't, because of the biasing conditions of the transistors will change in all practical circuits little bit. So it will result in small output change. Is it okay?
So is it related to VDD variation that we
yes,
have seen?
Power supply is VDD variation only.
So here we are keeping these two input differential signals to like same value. So we have seen that for differential signals, differential output, it should be 0. Like advantage of differential inputs.
No, I am saying when see what is an APS, power supply gain. Okay, power supply gain is when I give the same input. Okay, suppose I give it ground because I am giving plus and minus. I give 0 0, output should be 0. But if I give a sinusoidal signal here, okay, I will find a small sinusoidal signal here.
Okay.
Okay, that comes because the gain of the transistors will change. Okay, because of the power supply at various stages of an op-amp. Okay, it should not happen. You try and design like that, but it will happen.
So in this op-amp, sir, this is single-ended output.
Yeah, single-ended output.
Okay, that's why. I was thinking like it's we are taking differential no. Output. Okay.
So there could be these kind of outputs available. So that is why and then if you divide the differential gain with the power supply gain, then you get something known as power supply rejection ratio. Okay, so that should be as high as possible. APS, the gain of the power supply should be as low as possible. Okay, then I can have input offset voltage. I should apply some input offset voltage to get the V out 0, because while fabricating, because of various mismatches, it will happen that if you give the same input 0 0 say here, okay, you may not get an 0 output out here. Okay, so there will be typically you have to give an offset of around on a 4 to 6 millivolt here, so that when in between, okay, that could be plus or minus. Okay, because you can't say ki where which fabric the plus side transistor has got fabricated differently or the negative side. So in the op-amp specification they will say, okay, this is not divided by, it is minus. Okay, so around 4 to 6 millivolt. So they will specify it could be 4 to 6. So it could be either plus or minus. Okay, so that much voltage will have to be applied. Okay, at the input side, so that you get, if you are if you are doing some precise instrumentation, okay, then you might want to give this kind of offset voltages, so that this is 0 out here. Okay, now when I talked about 741 IC, there are some pins which Syed wanted to know what is 5 and 1. So we can use a small potentiometer between those terminals and adjust this output voltage to 0. Okay, that is internally the 741 allows us to give some offset voltage, so that this output is 0. Okay, is it okay with all of you? What is input offset voltage?
Yes, sir.
Okay. Now similarly,
Sir,
yeah, tell me.
sir, one question, like in previous slide, like how at high frequency this PSRR is getting reduced?
Actually, if you see the biasing network, okay, when the frequency, the VDS supply is very large, okay, they will take, because there are they take their own time to react to that signals, and hence that much of variation will not be seen. So the DC operating points, they are all DC operating points. So a small variation will start getting reflected easily rather than a fast signal. Okay.
Okay. Yeah.
Okay, because it is the basically the DC operating point of the transistors get changed, and for small signals it affects a large, whereas for high frequency that much it may not be able to follow that much. Okay, because of the capacitances involved in the which set the capacitances of the various transistors which are involved in setting up the bias conditions. So they will not allow that fast variation, and hence that won't get affected in the output. So that is that. Okay. Okay, input common mode range, I think that we saw for a differential amplifier. It is same. It is that common mode input voltage variation which does not affect the significant variation in the differential gain. Okay, that means as long as the transistors involved are in saturation, okay, that common mode input range which we did right for so many problems, so that will ensure that that much of common mode voltage this op-amp can handle. So that will also be specified. So if you go beyond the range which is specified, then the differential gain will affect, and also non-linearity also will set in. So that is the issue. Okay, then output voltage swing. Okay, so like output voltage is like, suppose you have a plus minus. So you suppose this is a pure sinusoidal. I am giving an plus 15 volt and minus 15 volt, and I am taking an output of plus 5 minus 5, that I might get a pure sinusoidal. Okay, but if you are trying to operate it close to plus 15 volt, so it might go there and go at least slightly rounded off. Okay, it will get, so these are all known as non-linearities which will come. Okay, so it won't be pure sinusoidal here in these areas. Okay, so slowly non-linearity will get in. So that voltage, output voltage swing is for that particular. So it is not output voltage. If the power supply is plus 15 and minus 15, generally they will say, okay, you can operate from plus minus 13 volt at the output. Okay, so that you get a linear output. So you should not try to achieve target an output which is close to VDD and minus VSS. So that specification also will be given. Okay, and then something, you have an equivalent input noise. Okay, so when I talk about op-amp, inside there will be so many transistors, and each of these transistors will generate some kind of noise. So at the output there will be some noise. Okay, and generally that noise divided by the gain, we call it as input noise. Okay, so obviously the signal which is coming here, that has to be much higher than the V in, and that is why we generally refer that output noise to input noise. Okay, so this ratio, this signal to noise ratio should be large enough. Okay, only then output there will be good signal to noise ratio. So although the noise generated within the amplifier will be seen only at the output. Okay, this noise is not an actual noise here. You can't measure this noise here. You can measure only this noise. You can see this noise at the output, but we are referring this noise to input okay, by V out divided by gain. Okay, that is known as input referred noise. So when you are referring it that to the input, and what is the advantage of referring to it? Because it gives a reference that, okay, if this is around 1 nano, this is typically for 40 to 50 nanovolt, this is the noise. So I will say, okay, my signal should be in at least in few micro, it should be around 2 microvolt or 1 microvolt above. It should not be in nanovolts, because the noise itself is available here will be in 40 to 50 nanovolt. Okay, so that is the reason. Okay, that is equivalent input noise. Okay, now what are these? So for low frequencies, I will have large noise, and for large frequencies, this will come down. Okay, so in our last lecture will be on noise. Okay, so we will see what are the sources of noise in MOSFET, what are the various kinds of noise. Okay, that we will see later on. So time being, we just understand that at low frequencies the noise will be more, and then subsequently the noise will become stable. So this is the kind of graph for noise. We will see that when we study about noise. Okay, so time being, let's say this is the equivalent noise, one of the specifications of the op-amp. It will give us the equivalent noise input. Okay, so what is the importance of this is that you have to ensure that your signal is much higher than the input noise. Okay, you can't expect good signal output here by giving 1 nanovolt input signal, because noise itself is 40. Obviously it has to be in microvolts, so that this noise is much lesser as compared to the input signal. Okay, so these are some of the specifications. Now, okay, a unity gain frequency, that actually is a measure of the bandwidth of the right. If you talk about a normal op-amp, okay, bandwidth we saw it is going to come like this, right? So when the gain becomes 0, okay, the bandwidth here, that is Ft, that is known as gain becomes 0 means in dB. Okay, dB 0 means it is what, dB is 20 log like 1. This gain is 1 log 1 is 0, right? So 0 dB, when we say 0 dB corresponds to whenever the frequency, so that frequency is known as Ft. Okay, so the Ft, so that actually tells us how fast this, if higher Ft means it is going to operate faster, and it is going to handle more higher frequencies. Okay, so we have to target Ft as large as possible, but that is not actually possible in many cases. It is only few megahertz we can have. Okay, we in fact try and make some dominant pole, and we try to reduce Ft. We will see that in circuits in the next class when we talk about stability. Okay. Okay, so we will see that phase margin. Okay, phase margin is also it is when the gain is 0. Okay, what about the phase? Okay, is it close to 180, or it is if it is close to 180, it can result in oscillations. So the difference from 180, how far it is from 180, and that is known as phase margin. Okay, so it has to be 60. So timing, don't worry much about the phase margin, because in the next class I will talk in detail about when we talk about a phase margin, about stability. I will speak in detail about a phase margin. Okay, so these are the two others. So if you have a large phase margin, it means it is stable. Timing, just remember that much. Large phase margin means it is generally 60 and above you should have. Okay, so so that means a smaller phase margin means it will cause ringing at the output. Okay, so that means instability will set in. Similarly, large Ft means, okay, that means the op-amp is good at high frequencies. Okay, it can give good gain at high frequencies. Okay, so and it will the slew rate will be better and things like that. Okay, so that you can this is bandwidth and this is stability. Okay, so these two things you need to remember. Okay,
Sir,
now
one doubt.
yeah, tell me.
So, sir, significance of phase shift is only to find phase margin, or is there any other significance?
No, phase margin is a measure of the stability, right?
Okay. So, sir,
Once we
what
give
is
negative feedback, okay, we'll see that in detail in the next class.
Okay.
Yeah, but you can ask me your basic doubt. Yeah.
So, so what is the physical significance of this phase shift that we find for any amplifier?
Okay. Now, suppose this is a positive signal out here, right? I have a feedback network here. Okay, I have some feedback network here. Now, so and I am giving a negative signal here. Now, suppose this signal, by the time it is coming from here to here, okay, it makes an 180-degree phase shift. Suppose it makes an 180-degree phase shift. Okay, I have some RC network somewhere here which is giving me feedback. Now, suppose that is introducing a 180-degree phase shift. Okay, so this signal will come as negative out here, right? It is a negative feedback system. Still in the feedback loop, okay, if it is going to introduce 180-degree phase shift, okay, then this signal and this signal, if I subtract, will they add? They'll add, right?
Yes,
now,
they will add.
They will add, then the signal will go, then this will reach saturation. Correct?
Correct.
Now, sometimes even if you don't give any input signal, there will be some noise. Okay, that noise will get amplified and you will find there is some oscillations in the output. Okay, so I want this not to be 180, it should be as low as possible, say 120 or something like that, right, for unit. So this 60 is the deviation from 180. Okay, so when for a unity feedback amplifier, okay, we'll see that. So it is just a measure of how stable it is. If it is close to 180, that means there is a very high chances that it will break into oscillations. Okay.
So, but sir, in negative feedback, we are expecting it to be 180-degree phase shift.
No,
because we are taking.
No, that is if you have a pure R network. But many a times, you will have R's and C's which is coming, right, and then it might result in phase shift also.
Okay.
Right. If I have to make an oscillator, okay, I'll do that. I'll put RC, I will put RC in the feedback, and I will ensure that it is 180 degrees.
Okay.
Okay. Then it will become an oscillator. Okay. We'll talk about all those things in the later class.
Sure. Okay.
So I didn't understood this FT. Can you explain that again?
FT is nothing but, suppose this is the what is, let me clear all this thing. Right, normal, what is the gain plot will be like this, right, in dB, right?
Yes.
In dB. So 0 dB corresponds to gain equal to 1, right? Isn't it?
Okay, yes.
dB is what? 20 log, right? A. A equal to 1. Log 1 is what? Log 1 is 0. So 0 dB means this is voltage follower, this configuration. So at what this is frequency versus dB plot. So this is FT, right? So if you have some other amplifier, okay, which is like this, okay, FT here, okay, that means it has got a better bandwidth, that's all. So FT is just a measure of bandwidth, you can call it.
Okay.
Okay, there are a few other terminologies associated with op-amp. One is slew rate. Okay, that is the maximum rate at which the output can change. Okay, so that is this is again divide. It has to be minus. Okay, not minus 2. Okay, 50 to 200 volts per microsecond. Okay, so we did that design of a differential amplifier, right? Slew rate. So slew rate comes from there. Okay, so depending on the current capacity and the load capacitance. Okay, so that is the slew rate. Okay, so slew rate will be the maximum slew rate is defined out here. Okay, so that the output will change. Now similarly, you could have an settling time. Settling time is whenever when a square input is step input is made here. Okay, at the output will go and get stable like this. Okay, so there will be some time, it will make an overshoot and then it will come and then it will get settled. Okay, so the time taken for it to get settled to the final 90%. Okay, a kind of 99%, usually within 1% of the final value. Okay, so that is known as settling time. Okay, so obviously when we do this feedback, all those kind things will happen, right? If there is no feedback, then it will, because it is an feedback, so there will be like for initially you are giving a step, this will go very high, then this will give a negative feedback, then it will come low, then slowly this will get in a stable where these two voltages will be equal finally, right? So whenever you give an steep input, so this kind of ringing will be seen at the output. That is known as the ringing at the output. Okay, so for that ringing to settle, so it will take some time, and that is defined as the settling time. Okay, now
so sir, is this the resonance condition that we are talking about?
No, no, this is like whenever you give a step input, because of feedback, it will the output will go like this, what is shown here. Okay, it will go and overshoot, and then it will undershoot, and then it will settle like this because of the feedback.
Okay.
Okay, so now you can give if you have learned control systems, you can set these parameters in the feedback in such a way that okay, it is doing an if it is not doing an critically damped, under damped, you might have learned, right? So if
Yes.
you are giving a step input, it is going and getting settled like this, it is known as critically damped. Over damped means it will go to
Oscillate.
and then it will oscillate, but it will be faster, it will settle down faster than this critical. And then undershoot means it will go slowly and it will not overshoot, but it will take lot of time. Okay, this is an ideal condition, but generally a slight overshoot is okay with us. Okay, because it will go and settle down faster.
Sir, can we have 10 minutes break? I
Yeah.
think we have been going for more than an hour.
Okay, okay. It is 44, 54. We will assembly back.
Okay.
Sir, any physical relevance like of having this as a property specification?
Settling time.
Yeah. Any example?
I would say in certain cases, if you are sampling this output voltage, suppose I have an sampling this with an say for a digital A to D converter. Suppose I am sampling this, right? So this sampling frequency should allow this settling time.
Okay, it should sample after this time.
Yeah, this kind of thing.
Okay.
So that kind of things can be. Now let's see. So first to make an op-amp, this is just a differential amplifier. So if I make an op-amp, if I consider this as an op-amp, obviously the gain will be right GM into R on this right. This is an N, this is P. So this we saw the differential. So what will be the drawbacks? Obviously the gain will be lower, one drawback, correct. Bandwidth will be lower because this is going to suffer from right Miller capacitance. This cannot drive low loads, high loads, okay, low resistances. Okay, so these are some of the drawbacks. It will have so these are some of some of the drawbacks, but this is a single stage op-amp. You can call this as a single stage op-amp, just a pure differential amplifier. Okay, now to improve that aspect, I can have a cascode structure here and a cascode mirror on top. Okay, so what happens now? Does the bandwidth increase? Anybody? does it have a better bandwidth?
Yes,
Yes,
because less linear capacitance.
Yes, from here to here there is no gain, right? So it bandwidth has now improved. Has the gain improved?
Yes, it is.
Yes, because now if you see from here, and right, it will be like an GM into RDS 6 into D8, right? So if you consider these are all equal, then it will be GM into R0 square, correct, impedance. Seeing into the bottom also, it will be same. So it will be GM R0 square by 2 kind of thing, and then you have this has a GM, one more GM, so that GM will also come here, right? So it will be like GM, but this, since this is an current mirror kind of thing, it will be just an GM RD square. This we saw, right, in the previous cases, in our previous classes also, right? So this is the advantage. Lower power consumption, obviously this is a stacked one above the other, so the currents are lesser. High input only one high input impedance node compensated with capacitance load if necessary. I'm not sure what they mean, but only one high impedance node compensated with the capacitance load if necessary. So this is a high impedance node, right, when you're seeing from here to here, probably that means. Okay. Now there is some drawbacks also. One is low output swing. Obviously there are 1, 2, 3, 4, 5 transistors which are stacked one above the other, so the output swing will be limited, right, because there will be some drops across each of these transistors which you will have to cater for. So low output swing. Reference of the input close to negative supply, that is this common mode signal. If you see here, it is close to the tail current, so and hence this on the negative side there is a very little margin. 2 bias voltages are required, okay, VB1, this one and this one, okay, and 5 transistors are in series, 1, 2, 3, 4, 5. So these are some of the drawbacks of having a single stage cascode amplifier. Okay, so let's try and improve this design. So you could have a mirrored cascode. Okay, now here if you see here, this is the tail current out here, and these are the 2 transistors out here, and there is a single mirror. Okay, now this current is being mirrored here, this current is being mirrored here. So this is what we learnt about the mirrored cascode, right? One folded cascode or mirrored cascode. So here this current is going to be mirrored here, and now this is flowing out here. Okay, this is again a common base, so output will be taken from here. Now here I have a cascode current mirror, so that the impedance is more. Now if you see here, in this path there are only 3 transistors where the signal is there. So I have the input common mode range is very high, and obviously here I had 5 transistors at the output stage, here 4 transistors, so it is better. Okay, so both the input common mode range has improved, output swing has improved. Okay, the drawbacks will be these. Okay, speed of the mirror, because this current has to get reflected out here. So at high frequencies all this will add additional capacitance and it will slow down the circuit. So that is there. Higher power consumptions, because you have now multiple paths. You have one path here, you have one path here, and you have one more path here. Okay, so 3 DC operating paths. Okay, so power consumption is higher as compared to only 2 paths here. So that is why. Okay, so I want you to do this analysis. Okay, what they are saying is, I picked it up from one textbook. So just see V out max. Okay, so let's do one. What is the maximum voltage available here? It can go. Okay, that is B1 max plus VGS and 4. It is saying this is the B1. Okay, this plus VGS4, okay, this voltage minus VSAT, okay, this is the overdrive voltage, okay, which is required for this particular transistor. Okay, so it can go maximum up to that. Okay, if it goes beyond that, then this transistor will come out of saturation. So that's how you set. I have one numerical, and we'll see that But these conditions I would want you to just go through that and verify whether these things which has been written out here is correct or not. Okay, you have to just see, you know, the conditions, whether these transistors are going in saturation, what is coming out of saturation. Okay, so that things you can verify. That is known as and then you could have a conventional folded cascode also. Now here again V in is given here. Now here I just have 3 transistors, and the output also, this is a cascode structure. Okay, conventional folded cascode which we did. Okay, again this mirror is also a cascode structure. This is also a cascode. So this signal is going to actually come like this. So this is a common source amplifier. This is a common gate configuration which is going to come like this. Okay, so these also, this is another way of implementing it. These are all single stage. Okay, so these are all the various variations of how to implement a cascode. Okay, so one drawback of all these is the load resistance has to be very high. Okay, so that drawback is there, but rest of the, because we are using cascode, we are able to increase the frequency, and by using like the folded cascode, you are able to get a higher headroom. So all those drawbacks are slowly improving when we are moving from one circuit to other. Okay, now
this is similar circuit to the cascode circuit we have seen in the common source.
Yes, correct. It is a similar circuit. So this is a 2-stage op-amp. Okay, now this is the first op-amp. Here if you see here, we are giving input to the PMOS transistors, and the load transistors are NMOS. Okay, so you are giving an input signal here. Okay, you will get an inverted signal out here, and then this is again a common source amplifier. Okay, this is again a current load which is seen from here. Okay, R06. So this is one stage of amplifier, differential amplifier. This is a differential amplifier, right? This is a common source amplifier. Here only the input is given to the PMOS and load is NMOS. Okay, it is the other way around. This is the current source, reference currents, which is used to bias these two transistors out here, right? So you get an output. What is the role of this CC? We will talk about in the next class. Okay, why do we have to keep this feedback out here? Okay, so that we will see in the next class. But otherwise, now what is the advantage of having 2-stage? If suppose this gain is around 15 to 20, you could achieve, right? Some of you could achieve 20 gain, most of you could achieve 10 gain. This is this also 10, so you will get around a gain of 100 when you are putting on a 2-stage op-amp. So minimum gain of 100 you can target when you are designing the circuit. Okay, so this you can probably try and implement it for your assignment. Okay, so you can target a gain of, because it is 2 stages out here, so you can do that. So this is known as 2-stage op-amp. Okay, so obviously again if you see here, this is not a cascode structure, so high frequency operation there could be an issue. Gain is now you can again okay, this is the derivation of the gain. Okay,
sir, I have a question in the previous.
Yeah, tell me.
So why it is floating there? The high bias is floating, the other end is floating.
Here?
Yeah, that one, yeah. Why it is floating?
This is floating, you are saying?
Yeah, why it is floating? I mean,
no,
like,
it is, when you show a current source, it means this current source is being generated by some circuitry, which will pull I bias here, which will be relatively independent of VDD and temperature variations. Okay, so these are known as band gap circuits. Okay, so this I initially wanted to cover it for your course, but I guess there is no time available. Probably if I am going to take advanced analog IC circuits, then I will talk about band gap reference there. Yeah, tell me.
For our assignment, so we need to have this I bias also, right?
Yes, you can have an I bias, and then probably you can give a ground out here. in that case. Or you can just simply connect a resistance here, right, instead of this current source, and you can get the desired currents.
Okay.
Right.
So
Now,
two-stage op-amp doesn't mean like we have to connect two op-amps in back to back.
just me. Yeah. Tell me, what is the question?
Two-stage op-amp doesn't mean like we have to connect two op-amps back to back.
No.
Or is it related to two stages of amplification?
Two stages of amplification. This is a differential amplifier. This is a common source amplifier, right? And I would want to have one common a source follower also, so that I can meet one more specification of op-amp of driving low loads also. Correct?
CD, common drain.
Yeah, common drain or source follower. Yeah. Right. Okay. So this is a two-stage op-amp. Okay. In two-stage op-amp, only the gain has increased drastically. Now, if you have to find out the gain of A1 and gain of A2. Okay. So gain of A1 is M1 into this resistance, right? M2 RO2 parallel to R0 4, right? So now that is in parallel. So R equivalent will be 1 by R1 plus 1 by R2. Okay, 1 by R1 you can write GDS1, and this you can write as GDS2. So R equivalent will be 1 by GS2. So that is why this has come in the here in this case it is an M2 and M4. So this is I have just taken a derivation example. They don't correspond to M1 and M2. Okay, so this is just an derivation. Okay, so this is in the side. So this has come to this resistance out here at this node. This resistance has come to GDS2 plus GDS4. Is it okay? This gain, first stage gain. Anybody has got any doubt here? The first stage gain. It's okay, is it? GM into R resistance. That's all, right? So R0 is parallel of M2 resistance as seen here, because this is the PMOS. And this is the NMOS is the load out here. So now same thing what we did for differential amplifier, M4 and M2. So at this node it is M4 and M2. So that is why it has come to. Similarly for this GM, right, and then M5 and M6. Okay, M5 and M6. Okay, so that you multiply with that. Okay, so that becomes okay. Now
so that is PMOS in between that. Previous M1 and M2 are PMOS?
Yeah, M1 and M2 are PMOS.
Okay.
You see the arrows which is going in. Right? MB, M7, M6, M1, M2 are PMOS.
We can implement by NMOS also, sir.
Then you have to give the load on top and biasing in the
bottom. Current mirror will be upper side.
Yes.
The down one will be upper side.
Yes. So this has been.
Sir, can you repeat which one is PMOS, which one is NMOS here?
Here M1, M2. MB, M7, M8, the arrow is pointing in, right? So they are all PMOS. These are NMOS. M3, M4, M5.
Okay.
Right? Okay. So that is a two-stage op-amp. Now, if you substitute the value of a GM1 as 2 mu1 COX W by ID, right? Similarly, this also you can substitute. Okay. So for GM it is these are PMOS, so it will be a mu P, mu N, right? So they will still be under the root. There is an COX for here and COX for these two, both COX. So COX will come out, right? And then root 2, so this 2 will come out. Where does this root 2 come in? I will tell you. So this gets replaced by this equation. Okay, for GM1 and GM. Okay, what is GS do is 1 by lambda into ID, right? So you go and this is what GS do is lambda into ID, right? So so you need to this will become lambda n plus lambda p. This will become again lambda n plus lambda p. So if you multiply, that will become lambda plus lambda p square, right? And these currents here there is one current, the same current is flowing in these two and same current is flowing in these two currents, right? So, this current and this current. So if you have to write a GDS, it is in a lambda into ID. Now what is ID is the current which is flowing here. That will be a ratio of this width of this and width of this, right? You have to find out the ratios, right? So if you put those ratios out here, you will get this equation. Okay. So this is again a home assignment. Just try to verify if you are getting this. If you are not able to get this equation, okay, then you can mail to me. I will request one of you to just do this derivation properly, and you probably can post it in the team. It is just simple, okay. Just substitute, write separately what GM1 is, what GM2 is, what GS2 is, what GS in terms of this is the equation for GM, right? And for GDS, it will be lambda into ID, correct? So those are the equations which you need to substitute. And where does this W by L ratio come? Because this is current mirror, right? So the ratio, this is I bias. So what will be this current? This current will be I bias into width of M4 divided by width of MB. So that W by L B, W by L this thing will come M7, right? So that is why this term has come here like this. Okay, so just substitute that and you will get this answer. It's pretty simple. So I will request one of you to do this and share it with everybody in the team. In the file section you can upload this. Okay, so you will see that this gain is there. So it will be better if you do it, because it will become easier for your exam. Okay, it is just a straightforward substitution only, nothing great about it. Okay, that is two-stage op-amp. This is about the two-stage op-amp differential gain. If I have to find out the common mode, okay, then this stage, okay, this stage, I will replace it with an half circuit. Okay, that way M1 and M2 will become in parallel here, right? I can just tell M1, and the current which will flow will be half of that. Okay, so I put on a 1/2 here. So this is a half circuit equivalent of this. Okay, now if you see here gain of this stage, okay, I am giving a signal here. I have one resistance on top and one resistance on the bottom. So gain of this, what will be the gain of this for the first stage? It will be just be this resistance divided by this resistance, correct? Let me write a point. Take a pen. Right, for an NMOS, if it is RD and RS, what is the gain? RD by RS, right? Now it is a PMOS in this particular case, so it will be this resistance divided by this resistance, right? So that is what is done here. Okay, and the gain of this is for the common, this is same, the gain will be same for a common source amplifier. Okay, so you get this this common mode gain and CMMR. So these three, please try to do it yourself, and one of you can share. It is straightforward only. If you are getting stuck, please feel free to mail me. So these are important from examination point of view also, and that is why I am asking you to try it out yourself once at your home. Okay, so this is one example. Okay, one numerical in which this two-stage op-amp is given here. The purpose of this CC we will discuss later on, okay, in the next class. But now we are trying to find out the DC operating condition and rest of the thing. So these are the parameters which are given. Width of all the transistors are given. Okay, of all the transistors are given. This current I reference is given as 90 micro, right? VTN, VTP is given. Mu n Cox is given. Mu p Cox is given. VA is given. Okay. What is VA? It is 1 by lambda. Okay, VA is nothing but 1 by lambda. VDS value is given, VSS value is given. Okay, now you have to find out. First we find out the DC parameters. Okay, so now this current, okay, this current is going to be 90, right? Now what would be this current? Now this will be like W by L 5 divided by W by L 8. This is Q8. Okay, so WL. So these are, it is given same actually, 8 is an 4 by 8, and a 5 is also a 40 by 8. Okay, so it is 10 times. Okay, so this current and this current it has to be 10 times larger. So ID 5, whereas here it is given same. So is there
So both are same, I think. So
Multiplied
5
by I reference should be there. I5 physical.
what happened? This is Q8 and Q5, right?
Q8. Okay, 10
Q5.
times.
Yeah, it should be 10 times. Probably this also should be 40 actually, probably. Right? Okay, so they could be an error. So we find out the currents. Okay, 90. So this becomes a Q7. Q7 is also, so this is actually yeah, this should be 40. Okay, or this might be 4 actually. Let's see. I think okay, so this is 4. So let's assume this also to be 4 out here. So then these currents will be okay. If it is other way, if there is a differential ratio, then the currents will be different. So you compute the currents. Okay. Now the currents in each of these branch will be in this branch will be half of it. Okay, because this current is equally distributed. So we come to know this current, right? And then we find out we overdrive. Okay, for each of this, half is there, mu n is there, Cx is there, W by L is there, right? So for transistor 1, 2, 3, 4, okay, it is 1, 2, 3, 4. This is 5. Okay, this is PMOS. Okay, Q3. Q3 and Q4 is NMOS. Q3 and Q4 is NMOS. Q1 and Q2 are PMOS, right? But then you have mu n and mu Cox are 4 times. The difference is 4 times. That means okay. Then that means mu n Cox into W by L is constant for this transistor and this transistor. Is it okay with all of you?
Yes, sir.
Right? This W, okay, of the PMOS, okay, Q1 and Q2 are PMOS, right? The W is 4 times the W of NMOS, right? And also the mu n is 4 times mu p. So that means the currents will be if the currents are same, then the overdrive voltages also will be same. So and hence this overdrive voltage for all the 4 transistors will come out to be 0.3. Is it okay? How this computation has been done? Okay. Similarly, this current is known. Now you will find overdrive of 6 and 5, right? Again, the current is known, mu n Cox and WL. If you substitute these values, you will get the overdrive voltage of this, right? So now if you see VGS for each of these transistors will be overdrive plus threshold voltage. So VGS of each transistors here, of each of these transistors for NMOS will be 1 volt, for PMOS will be 1.1 volt. Okay. So this is how we find the DC operating conditions of this particular circuit. So I'll share these slides so you can just verify these answers. Only thing is you can make this as 4. I think rest of the things will be okay. Okay. Either we make that as 4, or you can keep I reference as only 9. Okay. In both cases it will work fine. Okay. Then similarly finding out the AC parameters. Okay. Now you have to find out GM. So GM is 2ID by VOV, right? And you have to find GDS R0. So R0, this is the formula, right? VA by. So that is given here. So now for the first stage, the gain is A1 GM R2. So you will get the first stage gain. Second stage gain is GM6. This is 6, and R06 and R07 parallel. So this is, so you find you will get, and the total gain is multiplication of these two. Okay, so these are all straightforward. So just
Sir,
I have given one numerical example. Try to do this, and if there is any mismatch, let me know. Yeah, tell me.
Sir, what is VA?
What is
VA?
VA is early voltage. VA is 1 by lambda.
Okay, early voltage.
Okay, VA is 1 by lambda, right? So because you are having issues in the exam, so I thought, and I'll just put one numerical. All the values are given here. Okay, so you can do that, and then input mode, common mode range. Okay, now this is also given. Just try to analyze this. Now we have done a lot of analysis on the input range for a differential amplifier. Same thing applies here also. Okay, nothing different. The difference out here is a slight difference in thinking has to be there, because it is a PMOS out here. Okay, so when we increase this voltage out here, okay, this transistor will come out of saturation, correct? And if you decrease here, this transistor will come out of saturation. Okay, so those conditions needs to be catered for. So to support this current, you have to give minimum V overdrive voltage. Okay, so those kind of conditions, we have done enough of such kind of problems for the differential amplifier, as well as we have done such kind of analysis for the current mirrors also, right? So just go through those lectures of our current mirror. Okay, and then try to find out this the a maximum input range for this particular this. Okay, so this also you need to do it yourself. Similarly, the output range. Okay, what will be the max output range? Okay, for these two transistors. So when this is going up, it can come up to maximum overdrive, minimum overdrive voltage should be available here, right? So V aux will be V 2.5 VDD minus overdrive voltage of this. Similarly, when it is coming below, minimum overdrive voltage should be available here. So it is minus VSS plus overdrive. So it can come up to this range. Okay, so 0.3 margin you have to give. So for these transistors to be in saturation. So this is from plus 2.2 to minus 2.2. Okay, so this is important from your exam point of view. So this problem I have given here. If you do this problem, I think it will be good enough. Okay, because I took a problem which does all the analysis, the DC analysis. Okay, then it does the AC analysis, then it does the input common range, and it also does the output common range. These are only the four things which. So if you are comfortable with all these four formulas which has been used in this four parameter calculation, then I think you will be comfortable for your exam. Okay, so do that, and this is just to tell you, and a four-stage bipolar op-amp looks like this. Okay, finally, if you see here, there is something known as emitter follower, so that you can connect a low load also. Okay, with two stages, final stage has to be an emitter follower for low load, because that is one of the requirements of right, op-amp, right? So now here two sets of differential pair has been used, and then one common source. So you will find gain from here to here, here to here. Okay, for BJTs you can have higher gain. So each stage itself you can have close to 100. Okay, when you are using BJTs. So 100 it will become 20,000, and then again you can have one more gain out here. Then there will be a small drop of gain here, but then this will allow driving low transistors. Okay, so this is just to don't worry too much about this for your exam point of view, but just to give an indication of how four-stage bipolar op-amp. Okay, this is the circuit which is there in 741. 741 op-amp, it has got a BJT version as well as it has got an CMOS version. So this is the CMOS version. Okay, so there are a few 3-4 stages here. Okay, so there are some current protection mechanism, current sensing mechanisms also it's there. So it is not a part of our syllabus, and will not. We don't have that kind of time to do this full analysis. But then just for your information sake, I am flashing this slide. Okay, so timing, we will stop it here in this class. Next class we'll take up a new topic.